Last time we started taking a look at section 9.2, Multistage Experiments, and we had done a couple of examples. The first example we did actually had probabilities that changed each time because we were drawing names out of a hat, and so the names that were in the hat, and in particular the genders of the people in the hat, it fluctuated based on what my previous draw had been. And we talked about the fact that these events are what we would call non-independent events, or they're just not independent. Independent means that one draw shouldn't affect the others, right? Like if I roll a 3 on the dice the next time, I have just as much chance of rolling another 3. And that didn't happen when we had this example. We talked about our 5 slips of paper in a bucket and drawing out 2 of these. And this was an example of one where there's not exactly a tree diagram, but you are in fact writing out all the combinations of what can happen to make that work, all right? What else did we do? Oh, we looked at our spinner. And our spinner did have equally likely probabilities, right? So these are independent events. What I spin on the spinner the first time does not affect the second spin. What I spin on the first spinner does not affect what happens in the second spinner. These are independent events, and so you actually saw probabilities staying constant on this one, okay? So we're going to take a look at another example where the events themselves are simply not the same type of event at all right? So when I purchase a new shirt for my son, there is a 15 probability that he will stain it the first time he wears the shirt. If the shirt is stained, okay, so that's event 1. The event 1 is he stains it or he doesn't stain it. Are you with me? Then there's a second event, and it's laundry, all right? If he stains it, there is a 0.2 probability that I will not be able to adequately remove the stain. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? And the numbers are made up, but only sorta, you know? Like, we got issues with stains in my house. I don't know about your house and your brothers and sisters and so forth. But here's what we have going on. We have 2 events. The first event, we had said, is whether it gets stained. Now, you could say that there are 2 branches here off of each of these, and the question is whether or not it comes out clean or it's stained, right, after the wash. It's a little awkward to write it this way down here, although you certainly still could, because if it wasn't stained to begin with, then after the wash, it's not going to be stained again, right? So it feels a little bit funny, and if you want, you don't necessarily have to write this set of branches out, because it doesn't really apply. Do you see what I'm saying? There is a 1 probability that it comes out clean, and a 0 probability it comes out stained, from the context of what's happening. Are you with me? We're all good? Okay, good. Let's go back to the original stain, though. What is the likelihood that he stains the shirt to begin with? 0.15. And I chose this example as well so that you could see that we can do this with decimals just like with fractions, nothing specific. If it's a 0.15 probability that it's stained, what's the probability that he doesn't stain it? 0.85. And it's a reminder, as we're doing this problem, that each pair of branches have to add up to the number 1. It's one or the other. In language that we saw in number theory, for those of you who've taken that, these are complements of each other, right? They're exactly the opposite. They have to add up to 1. Now, if it's stained, what's the likelihood that I am able, well, actually, let's just use the phrase that it says here. It says there's a 0.2 probability that I will not be able to adequately remove the stain. So where does the 0.2 go? On which branch? Yeah, the branch that says it's still stained down here, right? Okay, I'm not adequately able to remove it. It's still there. And what's the likelihood then that I'm actually able to get it clean? 0.8. Okay? So this is the diagram that we're going to use to answer the question. The question it actually asks us is, what's the likelihood he wears it the first time and it's permanently stained from there on afterwards? And so if you're taking a look at our tree diagram, where am I if I'm going to answer that question? Where will I end up of the 4 answers over here? There's 4 branches on the right. Where will I end up? Yes, and so I will end up right here. Yeah? Yeah. And the way that I find the answer to the question then is by multiplying the probabilities along those branches. And we had that as a theorem last time. So I'd have 0.15 or 0.15 times 0.2, and that would give me what? 0.03. And whenever I get to that answer, I think that can't be real. Surely more likely than that in my house. But it's the right answer for the problem. Okay, any questions about that one? Okay, I mentioned this problem last time. We're going to do this one now. We've got Joe. Joe says if a family has 2 children, then the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? And explain. So the way we're going to analyze his argument is by drawing the tree diagram that represents what he's describing. A family having 2 children. Are you with me? Okay, so we're going to start with 1 branch. This is child number 1. And when the family has child number 1, there are only 2 options. It's either a boy or a girl. And what is the likelihood that it's a boy? 50%. So if you want to do fraction or decimals, you can do 0.5. If you want to do fractions, you can do 1/2. Either way works just fine. I'm going to go with fractions. That's only if they have 1 child, but they're supposed to have 2 children according to Joe's argument or what he's trying to argue about. So second time around, same thing. I will either have a boy or a girl. No matter what I had the first time, a boy or a girl. And each of these branches have a probability of 1/2 or 0.5, right? Because these events are independent. They're all 1/2s. So what I'd like for you to take a look at is that along each branch, I can actually see the top branch, I'm getting 2 boys. The second branch, I get a boy and then a girl. The third branch, I get a girl and then a boy. And the last branch, I get 2 girls. Okay? So the first part of his statement was that the only possibilities are 2 boys, 2 girls, or 1 of each. And that is a true statement, correct? I mean, all of the things that I just wrote down in these 4 categories are either 2 boys, 2 girls, or 1 of each. But they're not probabilities of 1/3. Why not?
Because there's more likelihood for the girl, for you to have a girl and a boy.
Yeah, because you can have them in any order, right? Yeah. So each of these branches, when I multiply along them, give me 1/4 probability. Everybody with me? 1/2 times 1/2, 1/4. So I have a 1/4 probability of having 2 boys and a 1/4 probability of having 2 girls. But I have 1/4 plus 1/4 or 1/2 probability of having 1 of each. Because I could have had boy or girl, or I could have had girl boy. So what are some of the things we would want to say to Joe? Well, he's not correct. Joe is incorrect. There are, one way to think of it is that there are actually 4 outcomes that are equally likely. And you could even identify them the way we did in our diagram. Boy, 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 girl, girl, boy, girl, girl. So probability 1/4 for each. But boy, girl, and girl, boy are both a boy/girl outcome. Let's try to do that. So the probability of one boy and one girl in either order, right, is 1/4 plus 1/4, which is 1/2. And the probability of two boys, which is what he was talking about, is 1/4. There's lots of other ways you could write down versions of what I've just said, but with the same idea. All right, any questions on that one? All right, it has been 3 years, I think, since I've taught this class in its full form. I taught it the very end for Dr. Marsh when she was on maternity leave last semester. So it's been a while since I've talked about this particular situation. So it's an opportunity that you guys get to learn a little bit about my family. We have a disease that runs in our family. It's called Huntington's disease. Has anyone heard of it before? A little bit? Huntington's disease affects your central nervous system. And what it does is as it progresses, it starts to shut down your ability to react to certain things. So your reflexes. So my grandmother had Huntington's disease, and some of the things that I remember as a small child is that she eventually lost the ability to drive because she couldn't slow down fast enough, and she'd have a minor collision with the car in front of her. Or we'd go to like a Golden Corral where they have the ice cream machines, and she couldn't stop the ice cream machine before there was ice cream everywhere. And what it is it's a chemical, not chemical, but it's a something. I'm not a science person. It's a something that your body overproduces that gets in the way of your body being able to do what it's supposed to do. It's an overproduction. And so my father also had Huntington's disease. In 2001, my parents actually decided to tell us that this is what Grandma had, and that my dad had been tested for it, and that each one of us had a 50-50 shot of having it. So I have one brother and I have one sister, and they decided to share this fun news on Thanksgiving that year. And at the time I was married, and my sister was as well. I'd been married for almost 3 years. My sister had been married for almost 1, and my brother was actually dating the woman that he ended up marrying a couple of years later. So this was like one of those serious family talk kind of things. And when they shared this information and knowing how it had affected my grandmother, the reason they decided at that point to share the information was because there had been new genetic research, not to cure Huntington's disease. There was that going on, but that's not what had been found out. But through in vitro fertilization, what they could do is they could create an embryo, they could grow it to 8 cells, and then they could test whether it had the Huntington gene anomaly. That's the word I want, anomaly. And if it had the Huntington gene anomaly, then they would discard that embryo. And if it didn't, then they would choose to implant those embryos instead. And so because of the genetic research, my family felt that it was the right time to be able to share that with my brother, my sister, and I, because we were all at that age where we were starting to consider, children in our future. And so we're going to look at this potential situation and what ran through my mind that night. Thanksgiving, we weren't living in Oklahoma at the time. We were living in Kansas, and we were visiting, so we were actually staying at my old bedroom, my house. And I'm going to show you what I did in my mind. I didn't do it with a tree diagram because that's not how I thought about it, but I want to show you what actually went through my mind when we were doing that. So, like I said, there's three siblings in my family. And the first sibling is me because I'm the oldest. And so there are two possibilities. You have genes that you get from your parents. One gene comes from my father and one gene comes from my mother. And my father had this gene that had the ability to either have the disease or not have the disease. So no matter what I got from my mom, it wasn't going to affect anything. It was one of the two from my dad. And what it does is it counts, there's the specific gene called the Huntington gene, and it counts triplet repeats, A's and C's and G's and T's, and I don't remember all the science behind it. But if the count is too high, then you will have the disease. It's not something that you can progressively get worse on or something like that. But if I got that gene from my father, then I would have it. And if I got the healthier number from my father, then I wouldn't. So I have two possibilities at that time. I either have the disease or I don't. And so that's me. I am tree branches number 1. And my sister is the next. She also has those same two chances. Chances that she either has it, or have it, or whatever we use, or she doesn't. So she will either have the disease or she would not. My brother is third, and he again would be my third set of branches. And again, he either has it or he doesn't. All right, and like I said, it's a 50-50 shot. So every single branch in this tree diagram has a probability of 0.5 or 1/2, okay? So put 0.5s or 1/2s in everywhere. I did 1/2s last time, so I'll do 0.5s on this one. Question A is the question that was in my mind that evening after my family had shared this news. The question was, in my mind, what is the probability that at least one of the three of us has it? What's the probability that this goes on another generation? What's the probability that myself, my brother, or my sister ends up suffering the way that my mom, my grandma, and eventually my father also did? My father passed away 4 years ago from the disease, and the end of his life was not good. He basically lost the ability to swallow, and a lot of those motor skills that you just don't have when you get to the end of this. So if you take a look at this particular tree diagram and you look along every branch where one of the three of us says that we have the disease, it's almost every branch, isn't it? In fact, the only branch that is free and clear where none of us have the disease is the very bottom. So in my mind, what I did is I actually said, well, there's a 50% chance that I have it, and there's a 50% chance that my sister has it, and a 50% chance that my brother has it. And so that's 1 minus that chance is what the likelihood is that at least one of us has this disease. So what is 0.5 times 0.5 times 0.5? And what is 1 minus 0.125? So I remember in our room that evening telling my husband this number. There's an 87% chance that one of my brother, my sister, or I has this disease. And that's a really scary number because that's big. You know, if somebody told you had an 87% chance of dying if you jumped out of an airplane, you would not jump out of the airplane, right? It's a big number. And it was really scary. So that evening, that evening, literally, my husband and I looked at each other and said, we're not comfortable with the in vitro fertilization for this purpose, for the purpose of eradicating this disease, because we feel like that's playing God. For us, that was our decision. And so we actually decided that we would be tested. I would be tested. And if I had the Huntington gene, if I had that disease, everybody has the gene, but if I had the disease, that we would not have children. It was not a popular decision for my family. They did not like hearing those words. It was really hard for my mom because she felt like, but if I had made that decision, you know, if your father and I had made that decision, we wouldn't have had you 3 kids. And I said, that's true, but I don't think you can look at it in retrospect like that. I think you can only look forward into the future and say what you're going to do with that knowledge moving forward. And so it took 2 years before we actually got to the point where we had decided we're ready for me to be tested. We're ready potentially to start our family. We'd been married for 5 years at that point, and I was really young when I got married, so I was still young at the point when I got tested. But God really used that time frame in between to tell us that it really didn't matter whether the results came back positive or negative, that adoption was in our future. It was very, very clear to us. But that was the catalyst. That is where and when we got started thinking about, what if I don't have children biologically? What about that? And we decided, well, we'll adopt, and we're okay with that. And so that was actually our first sort of movement in that direction. In 2003, I was tested for Huntington's, and I don't have the disease. Because I don't have the disease is why I have Abby. Abby's my 14-year-old daughter, and I'm very grateful, obviously, for her. I wouldn't change anything about that. But it's also the reason that literally 2 days after I had accepted my position and we'd moved to Ohio for my very first teaching position, we mailed off paperwork to an adoption agency to adopt our son. So, you know, because of Huntington's is also the reason that I have my son, and then I ended up at OBU and found, I guess, 2 teenagers that needed us, and we have them. And some of you were around when this happened 2 years ago. But 2 years ago, I had a miscarriage. We were not planning on having any more children, and found out that I was expecting, and I thought I was about 12 weeks along, 10 weeks along when I had my first appointment, and we found out that the baby had never progressed past 6 weeks, and that while my body had not miscarried yet, I had miscarried. And God used that too, and we now have 2 foster kiddos that are a part of our family, and we intend to keep. We'll see how that all turns out. But I would like to encourage you that even in those hard things, you know, I don't look back and look with fondness on this disease. My dad suffered terribly, and so did my grandmother. But I am grateful for God taking that and using that for good in my family. My siblings have never been tested. I have a sister who has 3 children, so they would all be what we would consider at risk. I have a brother who has 2 children, also at risk. And so I want to do the last part of this problem, and it says what is the probability that at least one of my siblings has Huntington's. And if you take this diagram and you eliminate the fact that I don't have it, that means that you're down here at this point, right? Because I don't have it. Then we just have a 2-stage tree diagram. And we can do the same argument that I did when I was talking about it being all 3 of us, is that I can do 1 minus the 0.5 probability that my sister has it and the 0.5 probability that my brother has it. And the number is smaller. It's not a lot smaller. There's still a 75% chance that at least one of my siblings has this disease, and that their children might as well. So I usually like to end this lesson and just let you guys ask questions if you had any questions that I didn't kind of answer, because it's kind of a personal story for me. So. All right. Well, if you think of anything or you want to talk, I'm here. We have group work for this section, 4 problems, 4, 3, 8, and 15.